Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A-Level Chemistry Unit 3 for January 2020. Let's begin with the first question. Question 1. Tests were carried out on some pairs of compounds. Bromine water was added to separate solutions of sodium chloride and sodium iodide. State one different observation for each reaction. When we add bromine water to sodium chloride, you could say there is no observation because there is no reaction that takes place. However, because bromine water is going to be orange or brown, when you add it to the colorless sodium chloride solution, the solution will turn brown or orange due to the introduction of bromine. But because there is no reaction, you can also say there is no observable change. So two answers are acceptable. 1. The colorless solution turns brown or orange, or no observable change. The next part. Addition of bromine water to sodium iodide, a reaction will take place because bromine is more reactive than iodine. This will actually be a displacement reaction. You will get sodium bromide and iodine. So iodine will remain in solution and the color of iodine solution will be observed. Since iodine in solution is going to be brown or yellow-brown, that will be acceptable. But also, there is observation of having iodine solidified, so you could say a gray solid could also be observed. Moving on. The next question says, name a test with the expected observation to confirm the presence of sodium ion in these compounds. So of course, sodium ion is confirmed with a flame test, and the color of the flame is going to be yellow. The next part says, barium chloride solution and hydrochloric acid were added to separate aqueous solutions of ammonium sulfate and ammonium nitrate. This is state what will be seen for each compound, which would allow you to distinguish between them. When we add barium chloride to ammonium sulfate, of course barium sulfate is going to be formed, but our observation is going to be a white precipitate. I wrote some of these reactions down here. You can see this is the reaction that will take place. However, these answers here are not required for this question. I just wrote them there so that you can see what is going to happen. So the white precipitate is going to be due to formation of barium sulfate. When we add barium chloride to ammonium nitrate, everything is going to be soluble from the reactants to the products, so we can say there will be no observable change. Moving on. The next part says, give a test with the expected results to confirm the presence of ammonium ion in the ammonium compound. So to confirm the presence of ammonium ion, you could add sodium hydroxide and warm or heat. Here the observation is when we use damp red litmus paper, it will turn from red to blue. In part C, acidified potassium dichromate 6 solution was added to 2 test tubes, each containing a different alcohol. The test tubes were placed in a warm water bath. The alcohols were, we have propan 1O and 2-methyl propan 2O. Of course, this is primary and that is tertiary. They say state what will be seen for each alcohol, which would allow you to distinguish between them. Because acidified potassium dichromate oxidizes primary alcohol, a color change is going to be observed, which is orange to green. But tertiary alcohols cannot be oxidized, so there will be no observable change with that. The next part says, give a chemical test with the expected observation to confirm the presence of a hydroxy group. A hydroxy group can be confirmed using PCl5. When we use PCl5, misty fumes are going to be observed. And when we use sodium, effervescence is going to be observed. Now, in this case, actually, in some questions, they'll ask you to write the equations for this reaction. So I want to try to give you an example here. Assuming that the OH is for an alcohol, we can say ROH for alcohol plus PCl5. We will get RCl plus POCl3 plus HCl. So the misty fumes are going to be due to formation of HCl. If it's over carboxylic acid, because you know those also have OH group, it will be RCOOH plus PCl5, giving us RCOCl plus POCl3 plus HCl. Again, the misty fumes will be due to formation of HCl. Another thing we can use is using sodium. When we use sodium, effervescence is going to be observed. Now I'm going to erase those reactions to create space for the reactions for sodium. What if we did the same reactions, but instead of PCl5, we used sodium? So this will be with sodium. We will get R or Na plus a half hydrogen, and this will be our CO, then ONA, plus a half of hydrogen gas. So you might be required to write those reactions. Please make sure you can do them. In part D, they say acidified potassium manganate 7 solution was added to separate test tubes containing samples of hexane and hexene. The test tubes were shaken gently. State what will be seen for each compound, which would allow you to distinguish between them. With hexane, there will be no reaction, and we will observe two layers. One of the layers is going to be purple, that is the layer with potassium manganate or the aqueous layer, where the hexane layer is going to be colorless. With hexane, because acidified manganate 7 interacts with alkenes to produce diols, and those diols produced are going to be soluble, the only observation we're going to see is we will see one layer in the end, and that layer is going to turn from purple to colorless. So this brings us to the end of question 1. Let's continue to question 2. Question 2. A class of students carried out experiments to determine the enthalpy change for the reaction of magnesium metal and hydrochloric acid. The following method was used. In step 1, a 1 meter length of magnesium ribbon was cleaned using sandpaper, weighed and cut into 10 centimeter lengths. In step 2, 50 centimeters cubed of hydrochloric acid, which is an excess, was placed into a polystyrene cup and the temperature was measured. And in step 3, a 10 centimeter length of magnesium ribbon was added to the hydrochloric acid. The solution was stirred gently and the maximum temperature was recorded. So from the table of results, we can see that the mass of the 1 meter of magnesium ribbon is 0.86. The initial temperature was 21.4 and the final temperature was 29.2. So we can see this was an exothermic reaction because temperature increased, and the delta T should be 29.2 minus 21.4. So I said, calculate the number of moles of magnesium in the 10 centimeter length of ribbon used in this experiment. So from the table of results, we see 1 meter is 0.86, but 1 meter is 100 centimeters. So 10 centimeters should be that divided by 10, which gives us 0.086 grams. So the number of moles are going to be the mass divided by the atomic mass of magnesium. And therefore, I got that, which I rounded off to 3.54 times 10 to the power negative 3 moles. Continuing on. Here they say, calculate the enthalpy change for this reaction, including a sign and units, and give your answer to an appropriate number of significant figures. Here they've given us the data. Specific capacity of the solution is 4.2, and the density of the reaction mixture is 1 gram per centimeter cubed. So before I calculated, I found the delta T, which is 29.2 minus 21.4, and I got 7.8 degrees Celsius. The Q, which is the energy release or heat release, is going to be mass of the hydrochloric acid times the specific capacity times the delta T. Now, since they've told us the reaction mixture has a density of 1 gram per centimeter cubed, it means 50 centimeters cubed is also equal to 50 grams. So the mass I used is 50 times that specific capacity times the delta T, and I got 1638 joules. To convert that to kilojoules, you divide by 1000, and I got my Q as 1.638 kilojoules. Now to find delta H, which is equal to Q over N, and again this is an exothermic reaction, so I put a negative. So I brought the negative Q, which is that, divided by the number of moles. In my calculation, I did not bring the rounded off moles. I used the value that was in my calculator. So this, which is that, divided by the number of moles from the previous page, I got negative 463 kilojoules per mole. And again, my answer, I rounded off to 3 significant figures because most of the things were in 3 significant figures. However, if somebody wrote in 2 significant figures, that would also be allowed because we have the heat capacity and the density given in those values. Here they say the maximum uncertainty each time the thermometer was read was plus or minus 0.1 degrees Celsius. Calculate the percentage uncertainty in measuring the temperature change in this experiment. Since the thermometer is read twice, the percentage uncertainty is going to be 2 times plus or minus 0.1 divided by the measured value from the thermometer, which is 7.8, times 100, and this was my answer. Next they say, suggest one way of reducing the percentage uncertainty in measuring the temperature change without changing the apparatus or just repeating the experiment. and they want you to justify your answer. In order to reduce the percentage uncertainty, we have to make sure we measure a bigger value. So it means the temperature change has to be higher. How can we make the temperature change higher? It could be either by decreasing the volume of HCl used or by using a greater mass of magnesium so that more heat is generated within the same volume of solution, so that the error in measurement using the thermometer can be decreased. So I said use a large mass of magnesium to generate more heat change, or you could use a small volume of HCl so that the temperature change is greater. Moving on. In part C, one student carried out the same experiment but used a glass beaker instead of a polystyrene cup. State how this would affect the value of the enthalpy change obtained, and they want you to justify your answer. Now you remember a polystyrene cup was used by one student, and that is a better insulator than using a glass beaker. So the effect on the enthalpy change when you use a glass beaker is it is going to be less exothermic because heat will be lost to the surrounding from the glass beaker than in the polystyrene cup. In part D, explain why the magnesium ribbon was cleaned with sandpaper before being weighed. Magnesium ribbon had magnesium oxide on the surface, so the magnesium oxide not being part of the reaction had to be removed. If it wasn't removed, then its mass would be contained, yet it's not going to generate any heat for this reaction, and that would be an overestimated mass of the solid, and the overall enthalpy change would not be as expected. So I said to remove magnesium oxide. If not, the measured mass will be higher than the actual mass of magnesium present. So this brings us to the end of question 2. Let's continue to question 3. Question 3. An experiment was carried out to determine the purity of solid sodium carbonate. The following procedure was used. 4.89 grams of impure sodium carbonate was weighed and dissolved in distilled water. The solution and washings were transferred to a 250 centimeter cubed volumetric flask, and the liquid level made up to the mark with distilled water, and the flask shaken. A pipette was used to transfer 25 centimeters cubed portions of the solution to conical flasks. Each portion of the solution was then titrated with hydrochloric acid of concentration 0.200 mole per decimeter cubed. So this is the equation for the reaction. And they say the indicator used was methyl orange. State the color change at the end point. Hydrochloric acid was in the burette and sodium carbonate was in the conical flask. And we know sodium carbonate dissolves in water to form an alkaline solution. So it means in the conical flask, the solution was alkaline and we had methyl orange indicator in alkaline. So the beginning color is going to be yellow. However, at the end point, the color is going to be orange. The results are as below, and they wanted us to calculate the volume of HCl used. So this is just subtracting that to get that, that to get that, that to get that, and that to get that. It's quite easy. So they wanted us to complete the table and using appropriate titrations to calculate the mean titer. To calculate the mean titer, you have to find out which results are concordant. And as we can see, this one here is very great in comparison to the others. So this and this one none. The only concordant results were that and that. And to be concordant means to be within plus or minus 0.2 of each other. So it's only these two that were in that. So I calculated and divided by 2 to get 26.15 centimeters cubed. Let me write centimeters cubed as my mean titer. Moving on. Here they say calculate the percentage purity by mass of sodium carbonate. From the question, they gave us the information for concentration and volume of hydrochloric acid. So I'm going to begin by using that to calculate the number of moles of HCl. The moles will be concentration times volume. This is the concentration and this is the volume. I divided by 1000 to convert the volume to decimeters cubed, and my answer came out as that. Now to find the number of moles of sodium carbonate in 25 centimeters cubed of solution, we have to go back here and see the equation. We can see the ratio of sodium carbonate to HCl is 1 to 2. So the moles of sodium carbonate should be a half the moles of HCl. So here I said moles of sodium carbonate in 25 centimeters cubed should be 1 over 2 times that, which gave me this. Also the moles of sodium carbonate in 250, that is, remember the mass was dissolved in 250 from the question. So this is going to be multiplying this by 10, and I got that. So these are the moles of sodium carbonate in the 250 centimeters cubed, that is in the volume in which the sample was dissolved. To find the molar mass of sodium carbonate, it is 106 gram per mole. So finally, to find the mass, it's going to be, this is the mass in 250 centimeters cubed, it's going to be the number of moles times the molar mass, which gave me that times 106, and I got 2.7719 grams. And the percentage purity should be the mass of the actual sodium carbonate in 250 divided by the mass of the solid that was dissolved times 100, which gave me 56.7 if rounded off to 3 significant figures. So this brings us to the end of question 3. Let's continue to question 4. Question 4. Bromoethane can be prepared by reacting ethanol with a mixture of sodium bromide and concentrated sulfuric acid. Of course, this is going to be 50%. In step 1, they say 5 centimeters cubed of ethanol and 5 centimeters cubed of water are added to a round bottom flask, and the flask is placed in an ice bath, and 5 centimeters cubed of concentrated sulfuric acid is added slowly. They add it slowly because, of course, it's going to be an exothermic reaction. They said during this process, the flask is shaken gently. Explain why the sulfuric acid was added slowly. We know that this reaction is extremely exothermic, so slow addition prevents the speeding or boiling over of the contents within the flask. Then in step 2, 6 grams of solid potassium bromide is ground up into a fine powder using a pestle and a mortar. The powder is then added to the round bottom flask containing the ethanol and concentrated sulfuric acid. The mixture is heated. They say state why the potassium bromide is ground up to a fine powder and justify your answer. Anytime a reaction is carried out and the solid is ground up into powder, the aim is to increase the surface area so that the reaction can go faster. So I said to increase the surface area so that the rate of reaction is faster. This allows for faster interaction between the liquid and the solid when the surface area is high so that the rate of reaction can proceed faster. Moving on. Here they say, in step 3, the crude bromoethane formed in step 2 is distilled off. Draw a label diagram to show the apparatus used for this distillation. Include a thermometer, but no clamps or stand. The key thing is you have to make sure the drawing makes sense. They'll be looking for a round bottom flask. Again, marks were not awarded for putting anti-bumping granules, but I put them anyway. You must put the source of heat. You must position the thermometer with a bulb at the entrance into the condenser or towards the side of the condenser. The water has to be placed appropriately, water in here and water out that side. And then this one has to be placed in order to prevent pressure buildup. And then the collection vessel has to be placed as well. And again, my drawing is not the perfect one out there, but at least it shows you what is required, at least the key things that are required. Moving on. They say state how anti-bumping granules prevent bumping in the distillation flask. Anti-bumping granules will provide sites over which bubbles can form, or you could say nucleation sites for formation of bubbles, and this is going to promote even boiling. In step 4, the distillate from step 3 is transferred to a separating funnel where it separates into an aqueous layer and a layer containing impure bromoethane. So here they've told us bromoethane is in the lower layer and the aqueous layer is going to be on top. This shows us that bromoethane is denser than the aqueous layer. So down here they say state 2 physical properties of bromoethane that can be deduced from this diagram. One is, of course, bromoethane is a liquid at room temperature we can see. And then we can observe that because 2 layers form, these 2 liquids, which is water and bromoethane, are immiscible. And then lastly, we can see that bromoethane is at the bottom. That means it has a higher density than that of the aqueous layer. Next they say, describe how the aqueous layer could be removed from the separating funnel. So in this case, you put an empty clean beaker below the tap, open the tap, and slowly run off the bromoethane layer. And then get a new clean beaker and open and run off the aqueous layer. And you could discard the aqueous layer because our purpose is to remove the aqueous layer. Moving on. In step 5, after removing the aqueous layer, sodium hydrogen carbonate solution is added to the impure bromoethane in a separating funnel and the 2 layers separate again. State-wise sodium hydrogen carbonate solution is added to the impure bromoethane. Sodium hydrogen carbonate is added to neutralize or to remove the excess acid. So this is for neutralization of the acid. In step 6, the bromoethane is placed into a sample bottle and a drying agent is added. They say identify by name or formula a suitable drying agent. It could be anhydrous sodium sulfate, anhydrous magnesium sulfate, anhydrous calcium chloride, or anhydrous calcium sulfate. Any of these will be okay because this was just a 1-mark question. And finally, describe how the appearance of the bromoethane changes after the drying agent has been added and the mixture allowed to stand. When water is present in an organic compound, usually it's going to be cloudy. However, when water is removed, that is going to turn clear. So I said it becomes clear. So this brings us to the end of question 4 as well as to the end of this paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.